Hello everyone, my name is Beata Zjawin, and today I'll talk about work that I did while I was a student at the Perimeter Institute for Theoretical Physics in Waterloo in Canada. This work was done in collaboration with Elie, Wolfe and Spekkens. Currently, I'm a PhD student at ICTQT in Gdańsk in Poland, and what you can see here on my first slide is a drawing of an old city in Gdańsk. The title of my presentation is Restricted Hidden Cardinality Constraints in Causal Models. And because I will talk about causal models and causal reasoning today, I decided to start with the following quote. Shallow men believe in luck or in circumstance. Strong men believe in cause and effect. This is a very old quote by Ralph Waldo Emerson, and it somehow captures the importance of causal reasoning and of cause and effect. But today, with this presentation, I'll try to go a step further and show that strong scientists infer cause and effect, and that this is possible even in the presence of unobserved variables. So let me formally introduce graphical causal models. A causal model consists of two things: a directed acyclic graph, which I will call a DAG throughout this presentation, and a probability distribution over the variables represented in a DAG. An example of a DAG is shown here, and the vertices of a DAG correspond to random variables. Here we have x, y, and u, and the directed edges correspond to causal relations. So u influences x and y, and additionally we have a direct causal influence of x on y. Basic structures that we can find in DAGs are the following. First, a fork. Here, z is the common cause of x and y. In this case, we say that z is a parent of x and y. Second one is a collider. So here, x causes z and y causes z. In this case, we would say that z is a child of x and y. And the last one is a chain. So we just have an arrow from x to z to y, or in the other direction. We say that a path between x and y is blocked by a node z if x and y are connected by a fork structure in which the middle vertex is z, or x and y are connected by a chain structure in which the middle vertex is z, or x and y are connected by a collider structure in which neither the middle vertex nor any of its descendants is z. So, for example, here, we say that z blocks a path between x and y because it is a fork structure and z is the middle node, but in here this is not the case. So here z does not block the path between x and y. And now this definition of blocking a path will be important to introduce deseparation that is kind of the base of the result of this work. So let x, y, and z be disjoint sets of variables represented in a DAG. X and y are said to be deseparated by z if and only if z blocks all paths between x and y. Okay, so let's look at some examples. First, consider this DAG. So we have x and y, and a path between x and y is this one. So a path doesn't need to be directed. This is a path. And this path goes through u. This is a fork structure. So in this case, u blocks the path between x and y, and we can say that u deseparates x and y. Now here, we still have this fork structure, but we have one additional path from x to y that goes through here, and it is not blocked. So x and y are not deseparated. And now the important thing is that the notion of deseparation captures conditional independence relations in DAGs. So in here, u deseparates x and y, and it means that x and y are conditionally independent given u. Okay, now let me introduce one more definition not connected to causal diagrams that will be needed for the results that I will show you later. And it's non-negative rank. So let P be a non-negative matrix, and the non-negative rank of P is the smallest number R for which P can be decomposed into a positive sum over R non-negative rank 1 matrices. Okay, so let's put it in a more condensed form. So we have this probability distribution, which is a non-negative matrix. And what we can do with it is we can decompose it as here. So here Px is a row vector, this is a column vector, and we just have a sum over this rank 1 matrices. And you can see that this sum goes over Z from 1 to R. Now, the non-negative rank of a probability distribution is the minimum number R for which this decomposition is possible. Okay, so we can make a trivial observation that a probability distribution can be represented as a non-negative matrix. And because of that, non-negative rank can actually act as a measure of dependence. So let's say that the two variables, x and y, are independent. Then we can factorize the probability distribution over them like this. So we just have px times py. And here we can say that the probability distribution has non-negative rank 1. Okay, but as the correlation between x and y increases, so does the non-negative rank of their distribution. And based on this observation, we give the following proposition. Let P be a joint probability distribution on random variables x and y. Then the following two are equivalent. First, there exists a non-negative factorization of P with non-negative rank R. And second, P factorizes as showed here. And now this factorization means that x and y are conditionally independent given Z when Z has cardinality R. So here we just have the probability distribution of x given Z has some value small z, probability distribution of y given z that z takes this value, and the probability distribution over z. And once again, I emphasize that the sum goes from 1 to r, where r is the non-negative rank. Okay, so we have a connection between a non-negative rank and conditional independence. And now what I said at the beginning of my presentation is that in graphical causal models, conditional independence is captured by deseparation. So we can take this proposition and we can interpret it using causal reasoning. And what we have is the following corollary. The non-negative rank of the matrix P constitutes a lower band for the cardinality of a variable z that deseparates x and y. So if we have a probability distribution over two variables, the non-negative rank of this probability distribution is the lower z, is a lower band for the cardinality of a third variable z that deseparates x and y, or in other words, makes x and y conditionally independent. Okay, so this is the most important result in our work, and although it is just a simple equation, now I will show you how it can be applied to different problems. Okay, so let me start with the problem of witnessing causal influence. Let's start with the following assumption. We have two events, x and y, and they both have cardinality 3. We also have an unobserved common cause, u. It's a common cause of x and y, and it has cardinality 2. Based on this information, we can make the following causal hypothesis. Either the causal model over these three variables is represented like this, so we just have u as the common cause of x and y, or we can have u as common cause of x and y and an additional arrow from x to y. Now, given this information and the probability distribution over x and y, can we make a decision like which one of these two models represents causally what is going on in this system of three variables? So we can use the corollary, and we know that in this case, u deseparates x and y. Here, this is not the case. These two plots are actually the same that I used for explaining what deseparation is. So here, u blocks a path between x and y. We say that it deseparates x and y, and because of that, we can use the corollary that I showed on the previous slide, and we know that the non-negative rank of the probability distribution over x and y must be smaller or equal to the cardinality of U. So if we observe the probability distribution, we can just simply compute the non-negative rank and test it against this hypothesis, because although U is an unobserved variable, we know its cardinality. We made the assumption that it's 2. Okay, so we observe the probability distribution, we check if this holds. And if it does hold, we can still not decide which one of these two causal hypotheses holds. But if this condition is violated, then it must be the case that we have a direct causal influence from X to Y, which basically means that we witnessed causal influence in the presence of an unobserved variable, and we did it just by making an assumption about its cardinality. The second problem that this corollary can be applied to is the one called distribution generation. So this is something studied in the communication theory, and the problem goes like this. Suppose two parties, Alice and Bob, are responsible for generating random variables x and y, respectively, such that x and y have a pre-specified joint distribution. The question is, how much information must be communicated or shared to generate this probability distribution? Now, this problem, we know the solution to this problem, and it's usually studied in two different scenarios. So the first one is the one here, where we have a third party, here denoted by Z, that is unobserved, and it shares some random variable with Alice and Bob, which are here represented by X and Y. And based on the value of this random variable, Alice and Bob generate their variables, and the question is, how many bits must be sent by this third variable to each Alice and Bob for them to output the desired probability distribution. And the minimum number of bits needed to accomplish this task is called randomized correlation complexity. Now, this problem is also separately studied for this different scenario in which we don't have the third party, but we have Alice, we have Bob, and we allow for communication between them. So we still want them to output the desired probability distribution, but here we allow Alice to send a classical message to Bob. And the question is, how many bits Alice must send to Bob for them to output the pre-specified probability distribution. And the minimum number of bits that must be communicated is called randomized communication complexity. And both of these values, the randomized correlation complexity and randomized communication complexity, are known to be characterized by a non-negative rank, but usually you need like a little bit more calculations to show that, and it's not that easy. But you can see that using the corollary that we showed here is actually very straightforward. You just have to notice that in both of these scenarios, when we represent them causally, as I did here, Z separates X and Y. So we can say that the logarithm of Z is lower bounded by the logarithm of the non-negative rank of the probability distribution that Alice and Bob are supposed to output. So by definition, randomized correlation complexity and randomized communication complexity are given by this log of the non-negative rank of the probability distribution. So in this case, a causal take on the distribution generation problem just really made this result maybe not obvious, but kind of easy to get. Okay, so one last thing that I want to discuss will be focused around this, so the one with the common cause. And here I have a classical common cause that's unobserved, and I have these two variables, X and Y. But what if I want this common cause to be quantum? Okay, so when we talk about quantum systems, we don't really represent them as DAGs, as diagrams, right? We use quantum circuits. So the first thing that I will do is I'll kind of translate the DAG that I have into a quantum circuit. So let's say that I have a quantum common cause, rho C, and I want to send it to Alice and Bob. Well, the first thing is I cannot just copy it and send it to Alice and Bob, right? So I have to make some kind of decomposition, here represented by this white dot, which represents the decomposition operation introduced in this paper cited here. So I decompose the quantum common cause, and I send one component to Alice, row A, and one component to Bob, row B. Here, the double wires represent quantum systems. Then what Alice and Bob do is that they perform some measurements and they output classical variables A and B. So in this protocol, what we get at the end is a probability distribution over A and B. But yeah, just remember that what we had at the beginning is not a classical common cause, but a quantum one. Okay, now what if we allow for this direct causal influence between Bob and Alice? Then what we have is a quantum common cause that's shared between them. But now, when Bob performs the measurement, he can communicate his output to Alice. And then Alice, based on the knowledge of Bob's output and her share of the quantum system, outputs the classical variable A. So what we get in this protocol is the probability distribution of A given B. And we could ask a similar question to the one in the witnessing causal influence problem. So in the classical case, what we had was this DAG and this DAG. And we asked, okay, I have a probability distribution and I know the cardinality of the hidden variable. So what can you tell me about these two hypotheses? Like, can I say which one is the right one to describe my problem? So let's see if we can ask a similar question here, that I have these two circuits and I have a quantum common cause that I know a dimension of. This kind of corresponds to the cardinality of the hidden variable, and I want to know which circuit represents the probability distribution that I have. So to answer this question, I need to introduce one more definition. So let P be a non-negative matrix, and then the positive semi-definite rank of P is defined as here. So we have the probability distribution, and now what we do is we take its elements. So this is when big A is equal to small a, and each element of the probability distribution can be factorized as this, where E and F are both positive semi-definite matrices of this dimension. And if we can make this decomposition, then the minimum number R for which we can make this decomposition, where R is in the dimension of these two matrices, is called a positive semi-definite rank. So this is kind of an extension to what we had in the classical case, where we had a non-negative rank. Now, with a quantum common cause, we have a positive semi-definite rank. And it can be showed that in this case here, when we have no communication between Alice and Bob, and you have a quantum common cause, under the assumption that the dimension of row A and row B, so the subsystems sent to Alice and Bob, so when we assume that the dimension of them is D, we can say that D must be greater or smaller to the PSD rank, so the positive semi-definite rank of the probability distribution that Alice and Bob generate. So as you can see, this result is really similar to the one that we had in the classical case. But in the classical case, what we did is we had a broader corollary which talked about this separation. And it's not that easy, if even possible, to define this separation in quantum circuits. So it's not that straightforward how to translate our results to the quantum case. But because of this connection between the non-negative rank and positive semi-definite rank, we can say that our classical results kind of sets the stage for further explorations in the quantum regime. And this is all that I wanted to say for today. So yeah, thank you.